Hi, Chem 201 Organickers. Welcome back to another mini lecture. This time, this lecture is going to be about formal charges and resonance on Lewis dot structures. Again, from your prerequisite course that you took in order to get placed into this class, if you took Chem 121, you will have seen resonance and formal charge. If you took Chem 110 or Chem 100, you may or may not have actually seen about formal charge and resonance. So what I want to do is just introduce the concept, show you what we're going to need to know about it for organic chemistry so that we're all on the same page. And when we start talking about various charges as we go through these organic structures, that everybody knows what I'm talking about. So let's go and just look a little bit about resonance and formal charges in Lewis dot structures. So let me share my screen. So here's the slides, and we're going to talk about resonance and formal charges in Lewis dot structures. So I don't know if you guys have known or have noticed this or not as you draw Lewis dot structures, but a lot of times when you draw a structure, there are multiple structures that actually occur or that can be drawn that uphold all of the valid bonding rules for Lewis structures. So Lewis theory actually localizes the electrons between the atoms that are bonding together. Now we know through extensions of Lewis theory that there is usually some degree of localization of the electrons, and we call this concept resonance. Resonance is really important to organic chemistry. And when we look at if something is stable or not, resonance stabilization is going to be something that we talk about, because delocalization of charge, when there are charges, will actually help to stabilize the overall molecule. So when I can draw more than one Lewis structure for a molecule that differ only in the positions of the electrons, they are called resonance structures. The actual molecule in physical nature is actually a combination of the resonance forms, and that combination is called a resonance hybrid. The molecule does not resonate between the two forms, although we often draw it this way. When we want to determine whether resonance is available for a particular structure, what we're going to do is typically look for multiple bonds or lone pairs. So if you look at this molecule down here, this is O3, or ozone. And I can actually draw this structure both of these ways, right? If I could distinguish between this carbon or this oxygen and the oxygen here, what I'm going to notice in one structure, here I have two lone pair and it's attached to a double bond, and that's how I get the octet. Here I have three lone pair and it's attached to a single bond. That's how I get the octet. So those oxygens actually have a different bonding array. But if you notice between resonance structure 1 and resonance structure 2, the connectivity of the atoms is the same. The only thing that's different is the positioning of the electrons. And I can go from one to the other if I sort of rearrange my electrons using an arrow. So if I look at this lone pair, actually if I look at this lone pair, in order to get from 1 to 2, what I'm going to notice is I could put this in and make this double bond, but then because that would violate the octet rule on this oxygen, these electrons have to come out. And then if I do that arrow, what I'm going to see is that I go from resonance structure 1 to resonance structure 2. I could also go the opposite way And if I actually want to go from resonance structure 2 to resonance structure 1, I can dump those electrons here and put those electrons out on that oxygen. And then my green arrows will show the transition between 2 to 1. And my red arrows are going to show the transition from 1 to 2. And then the combination of those two structures, where I kind of have half a double bond, like a bond and a half. So I don't quite have a double bond, but I have more than a single bond between the two oxygen-oxygen bonds. That's what I would consider to be my resonance hybrid. So this is sort of what it shows. When I look at this, basically I have a bond and a half between each of the oxygens within the ozone. So I have two equivalent bonds as you can tell, because the bond length is the same in both cases. And basically the hybrid then is somewhere in between those two structures. And that's what I actually can see physically in nature. So here, you want to be able to indicate how you can actually go from one resonance structure to another using this arrow pushing molecule. So what I can do in this case is I can do a couple of things. I can go from this structure, I'll call this 1, to this structure. Notice I have 3 lone pair and a single bond on this oxygen. And then here I have 2 lone pair and a double bond on that oxygen. So again, if I do this and then I do this, I'm going to go from resonance structure 1 to resonance structure 2, and vice versa. If I do this and then I do this, I can go from resonance structure 2 to resonance structure 1 when I look at pushing the arrows that way. So what I have to do in order to draw resonance structures is I'm going to draw the Lewis structure. I'm going to look and see if I have lone pairs or double bonds that I can sort of move around by pushing arrows. And then I'm going to draw all the discrete resonance structures available to me that still obey the basic rules for Lewis structures. Now, let's look at this molecule, N2O. I can actually draw 3 resonance structures for this particular molecule, and they're all valid. And the 3 resonance structures I can draw are illustrated here. Which one is best? In order to determine which resonance structure of the 3 that I can draw for dinitrogen oxide, I need to actually consider something called formal charge. The formal charge is determined by looking at the difference between the number of valence electrons in the free atom and the sum of lone pair plus the one half of the bonding electrons in a molecule. If those two numbers don't agree, then that atom is going to have a formal charge. So for example, if I want to look at this nitrogen here, I know that nitrogen is supposed to have 5 valence electrons. But what I'm going to do is take the lone pair and I'm going to add half the bonding. So if I draw a line here, the lone pair is 2 electrons, half of the bonding is 1, 2, 3, and I end up with 5. Nitrogen is supposed to have 5, it does has 5. This has a 0 formal charge on it. Now let's look at this other nitrogen, right? I don't have a lone pair here, and I have 1, 2, 3, 4 electrons, it's supposed to have 5. So it has 1 less electron than what it's supposed to have. So this is actually a positive charge on that nitrogen. When I look at oxygen, oxygen is supposed to have 6 electrons. That's what it says according to the group number on the periodic table. But here I have 3 lone pair, which gives me 6 electrons, and then I have half the bonding plus 1, that gives me 7. So this particular oxygen right here has 1 more electron than it's supposed to have, which gives me a negative charge on that particular oxygen. So when I do this, what I'm going to notice is in a neutral molecule, the sum of the formal charges has to equal 0. If I have a charged species, like an ion, the sum of the formal charges has to equal the ion charge. This is neutral. So if I look at adding plus negative, I get 0. So my overall charge on the molecule is 0, even though I do have a positive charge on the center nitrogen and a negative charge on the rightmost oxygen, right? Now, if I look at these other structures, I can do the same thing and figure out what those are. Let's go back and just do a little bit of a more formal definition of what a formal charge is. Now, this is a fictitious charge, which is assigned to each atom in a Lewis structure. And this allows us, this helps us to distinguish among competing Lewis structures. I can evaluate the structures. The structure that is more stable, the structure that I assess to be better, is actually a larger contributing structure to the resonance hybrid. So in some regards, I can figure out what the atom looks like by just evaluating formal charges. Again, in a Lewis structure, I'm going to calculate an atom's formal charge just like I did above. And this indicates the charge it would have if all the bonding electrons were shared equally. The sum of all the formal charges in a molecule has to be 0. And in an ion, the total equals the charge. So here's sort of a formula. I'm going to look at, to determine the formal charge, I'm going to look at the number of valence electrons in the free atom. So this is off the periodic table. And then I'm going to take half of the number of bonding electrons. This is in the Lewis structure on this side, minus the number of non-bonding electrons, which are the lone pairs. So if you notice on this chart before, I go and I get, this is the one that we just did. The leftmost nitrogen is 0, the center nitrogen is 1, and the rightmost oxygen is -1. +1 and -1 equals 0, so that's a valid structure, right? If I look at this other structure here, I'm supposed to have 5 valence electrons because it's nitrogen. I actually have 4 electrons because I have 2 lone pairs. So I have 1, 2, 3, 4 electrons there. If I draw a line there, I have the number of shared electrons, which is 4. But if I just look at the 2 in this double bond and take half, that'll give me 2. So by my method and not using this formula, what I'm going to have is the number of lone pair is equal to 4 electrons. Half the bonding is equal to 2 electrons. That gives me 6 which is one more than it's supposed to be for nitrogen, which gives me that -1 charge. You can do it either way. You can follow this chart and you can go ahead and do this exactly this way, or you can do the way that I did it. So for example, we just did, let's do this guy. So this nitrogen is supposed to have 5. It's got 2, 4, 6 electrons in lone pair, plus 1 electron, that gives me 7, which gives me a -1 on this guy. Here I have half the bonding, no lone pair. So I have 1, 2, 3, 4. It has 4 electrons. It's supposed to have 5. So this is a +1 charge on the central nitrogen. And then this oxygen has 1, 2, 3, 4, 5. Oxygen is supposed to have 6. I have 1 lone pair, which gives me 2, and 3 electrons from half the bonding, which is 5. So this is a plus charge. Actually, this is supposed to be -2. Sorry. This guy has 6 plus 1 gives me 7. It's supposed to be 5. It has a -2. And I noticed that discrepancy because -2 plus +2 is equal to 0. And I know my formal charges have to be 0. Here, again, 1, 2, 3, 4, 5, 6. It's supposed to have 5, so it's a -1. 1, 2, 3, 4. It's supposed to have 5. That's a +1. 1, 2, 3, 4, 5, 6. It's supposed to have 6. That's a 0. So if I look at this, if I do it my way and just look at the Lewis structure and count the electrons around it, I can get these formal charges. The other way you can do it is actually use this formula. But what you're going to notice is that the formal charges are going to be the same regardless of what method that you use for an individual resonance structure. So here we've got these 3 different structures. I have a 0 on my left nitrogen, a +1 on my center nitrogen, a -1 on my right oxygen. I have a -1 on my left oxygen, a +1 on, or my left nitrogen, a +1 on my center nitrogen, and a 0 on this right nitrogen. Again, -1 plus 1 gives me 0, so that's fine. And then in this one, I have a -2 on the left, a +1 in the middle, and a +1 on the right, which -2 plus 1 gives me 0, so all these are good. So which one is the best resonance structure for this particular molecule? Well, I have to do an evaluation. So better structures have fewer formal charges. This one has the most formal charges. Each atom has a formal charge, and my nitrogen has a larger formal charge than in any other of the structures. So this one is actually not a very good structure. Better structures have smaller formal charges. So that leaves these guys, this one and this one, right? Those both have a +1 on a nitrogen, a -1 on an oxygen, and then in the center structure, I have a -1 on a nitrogen and a +1 on a nitrogen. So those are smaller than that rightmost structure. So I still haven't decided between these two which one would be better. So I'm looking at rule 3 then. When the negative formal charge is on the more electronegative atom, it's a better structure. So oxygen, in terms of electronegativity, is greater than nitrogen. So I want the negative charge to be on oxygen because that's the more electronegative atom. Here, if I have my negative charges, this one is on oxygen and this one is on nitrogen. So this structure is actually the best structure of those 3. I have fewer formal charges, I have smaller formal charges, and my negative charge is on the more electronegative oxygen atom. This one would be second, and this one would be third. This would be the main contributor for the resonance hybrid. So it's going to look in nature a lot more like this one than this one. And then this is going to have a little bit more of an impact than this one as well. So you might want to start thinking about how you're going to use this. Here I have the phosphate ion. This is PO3 minus 3. Actually, this is phosphite ion. So which one of these two structures is better? All right. So what I'm going to do is take each atom individually. This oxygen here is supposed to have 6. I have 1, 2, 3, 4, 5, 6. Half the bonding gives me 7. There's a negative charge here. This oxygen, 1, 2, 3, 4, 5, 6. Half the bonding is 7. I'm supposed to have 6. I have 7. This is a negative charge on that oxygen. 1, 2, 3, 4, 5, 6. Half the bonding is 7. I have supposed to have 6. I have 7. There's a negative charge there. Phosphorus is supposed to have 5. 1, 2, half the bonding, 3, 4, 5. So that gives me a 0 charge. So here I have -1 plus -1 plus -1 plus 0 is equal to a -3. Well, my ion charge is -3, so that's perfectly valid. All right, so let's look at this bottom structure so I can differentiate which one is the best structure for the phosphite ion. Here I have 6. I have 1, 2, 3, 4, 5, 6. That's 0. I have 1, 2, 3, 4, 5, 6, 7. That's -1. I have 1, 2, 3, 4, 5, 6, 7. That's -1. And I have 1, 2, 3, 4, 5, 6. It's supposed to be 5. So this is a plus, this is also a -1. So here I have -1 plus -1 plus -1 plus 0 is equal to -3. But where's my negative charge? Here I have 3 negative charges on oxygen. Here I have 2 negative charges on oxygen, 1 negative charge on phosphorus, and 1 oxygen is a 0 charge. Here, my phosphorus is the 0 charge. So what's more electronegative? Oxygen is more electronegative than phosphorus. So this structure is going to be the worst structure, right? Because my negative charge is on the least electronegative atom. So this is the worst structure. This guy is the best structure because my negative charge that's different between the two is on more electronegative oxygen. Now, remember when we talked about Lewis structures? If I obey the common bonding patterns, a lot of time those are going to give me structures that don't have a negative charge. So basically, these are all 0 charges because when I look at this, anything with carbon with 4 bonds is going to give carbon 4 valence electrons, so that's a 0 charge. With nitrogen, I have 1, 2, half the bonding, 3, 4, 5. It's supposed to be 5. That's a 0 charge. Oxygen with 2 bonds and 2 lone pairs is a 0 charge. And then the hydrogen and the halogen, generally they only form 1 bond. And if I notice that my halogen also has those 3 lone pairs, half the bonding is going to give me 1 and 7, which gives me a 0 charge on that atom. It's when I don't have the common bonding patterns that I have to look for charges. So the ones we really have to look for using our summary are these guys. Remember, I'm really interested in carbon, nitrogen, oxygen, and halogens. Those are the atoms that we're going to use the most in organic chemistry. So you can tell when I follow normal bonding patterns, I result in all of these different bonding arrays. So boron with 3 bonds, carbon with 4 bonds, whether it's 4 singles, a double and 2 singles, or a triple and 1 single, right? My nitrogen with 3 bonds and 1 lone pair, whether it's 3 singles, a double and 1 single, or a triple bond. The same thing with oxygen. If I have 2 bonds and 2 lone pairs, 2 bonds and 2 lone pairs, I'm going to get a formal charge of 0. When I change that, that's when I'm going to start getting charged species. So here, right, if I just look at that guy, carbon is supposed to have 4. If I look at half the bonding, I only have 3. So that's a positive charge. I have to be able to look at these different bonding patterns, these bonding patterns that don't really give me those normal bonding patterns, because when I have these, I'm going to have charges available to me. And notice here, right, lone pair, 1, 2, half the bonding, 3, 4, 5, carbon's supposed to have 4, it has 5, this gives me a -1, which is illustrated there, right? So here, notice, I have carbon that has less than 4 bonds, I'm a positive charge. I have extra electrons, I'm a carbanion, I have a negative charge. So it's the distribution of the electrons, the number of electrons around my central atom, that is giving me those formal charges. This chart is really important. You should probably know these different species, because these are the ones that are going to be commonly seen in organic chemistry. Carbon can be positive, can be neutral, and can be negative. So can nitrogen, and so can oxygen. And what we have to figure out is, based on the Lewis structure, where my charges are and what they mean for the overall structure. So this is a chart that you probably want to evaluate, make sure you understand why the charges are where they are. And then as we start going into organic chemistry and we start looking at positively charged carbocations and negatively charged carbanions, we're going to see how we get those charges and how that influences the chemistry of those compounds. So that's all I have for this guy. Again, as always, if you have any questions about anything, don't hesitate to contact me. And make sure that you understand these concepts at least a little bit, so that you can recognize them when we start doing our own organic chemistry deep dive in this course, as we start on Monday, June 1st. All right, see ya.